we will today complete the mathematical solution of adiabatic flow through a duct with friction. We have derived 7 equations and mentioned that in that 7 equations there are 8 differential parameter involved, and we will solve 7 of them in terms of the 8th one, and for that 8th one we have chosen the geometry of the duct and the friction force, because which is the governing or driving mechanism for this flow. We have seen that we have treated dx by d is the basic differential parameter and associated f with it. So, that f dx represent the friction force, and the 4 is also taken with it for convenience. So, with these 7 equations, instead of treating them as differential equation, we are treating them as linear algebraic equations and solving for the differential parameters or differential variables. Now, using that equation number 1 and 3. So, from equation 1, which was the differential form of the equation of state, and equation 3, which is the differential form of the energy equation, we obtain dP by P equal to d rho by rho minus gamma minus 1 by 2 m square d u square by u square. Now, using equation 4, we replace d rho by rho using equation 4, we replace d rho by rho and obtain dP by P equal to minus 1 plus gamma minus 1 by 2 du square by u square. Now, using 5 to replace du square by u square in terms of the friction parameter 4 f dx by d, we get one plus gamma minus 1 m square divided by 2 into 1 minus m square 4 f dx by d. Similarly, we can use various relation to obtain d m square by m square to minus gamma m square into 1 plus gamma minus 1 by 2 m square divided by 1 minus m square into 4 f dx by d. We number this equation as 9 and the earlier equation for pressure we number it at 8. Also, we can get du by u which is our equation number 10. The temperature differential dT by T, which is also related with the speed of sound, is gamma into gamma minus 1 m to the power 4 by 2 into 1 minus m square the density differential becomes the stagnation pressure become question 13, and finally, the impulse function solution is the change in entropy can be evaluated. Change in entropy can be evaluated as delta S by C p equal to log T 02 by T 01 divided by P 02 by to the power gamma minus 1 by gamma. Since we are considering adiabatic flow in this case, T 02 by T 01 is 1, that is there is no change in total temperature, and consequently we get d s by equal to minus gamma by d p 0 by p 0. Since T 0 is a constant in adiabatic flow. So, if we put dP 0 by P 0 from equation 13, if we put P 0 by dP 0 by P 0 from equation 13, we get ds by Cp equal to gamma minus 1 by 2 m square 4 f dx by d. Now, since entropy cannot decrease in an adiabatic flow, this seems that F must be positive or the shearing stress must act on the stream in a direction opposite to the direction of flow. What we have assumed in our analysis in the beginning. So, entropy cannot decrease in adiabatic flow, hence F must be positive, which implies that the shearing stress which assumed tau w must always act in the direction opposite to the flow. As was taken here. And we can see now from this relation that the isentropic stagnation pressure and the impulse function always decreases when friction is present, irrespective of subsonic or supersonic flow. So, from 13 and 14, P 0 and F always decrease if friction is present. If friction is present, that is for both m less than 1 and m greater than 1. And this implies that wall friction will reduce the effectiveness of all type of flow machinery, and it will also reduce the thrust that is obtained, that can be obtained from the jet propulsion device or the jet nozzle. Of course, jet nozzle is not a uniform area duct. However, this behavior remains the same, that is the presence of friction will always reduce the thrust that can be obtained, and it also reduces the effectiveness of all type of flow machineries. The remaining parameters, that is the pressure, temperature, Mach number, they however behave differently in subsonic and supersonic flow, which can be seen from these equations. Like equation 8 shows, P if we make a table for subsonic and supersonic, P decreases in a subsonic flow, dP by P is negative, and P decreases in a subsonic flow, however, it increases in a supersonic flow. dP by P become positive. Similarly, equation 9 shows Mach number dm square by m square is negative, and Mach number increases and decreases in this case. Similarly, equation 10 shows that U increases and in supersonic flow it decreases. Similarly, T dt by T is negative in supersonic flow, and this is decreases, however, it becomes positive in supersonic flow and it increases. Rho decreases in subsonic flow, but increases in supersonic flow. And the stagnation pressure and impulse function, they decreases in both cases. As already mentioned. So, this also suggests that Mach number in the flow due to friction always tends towards unity or sonic flow, and consequently the transition from one region to other region is impossible. That is, for a given condition at an initial section of the duct, the maximum possible duct length that can be employed without altering the given initial condition or without altering the mass flow rate or without introducing any discontinuity, the maximum length can be that for Mach number at exit is exactly unity. That is, when there is friction present in a short duct where the flow is approximately adiabatic, for a given total stagnation enthalpy and that is energy, and for a fixed mass flow rate, there is a maximum possible duct length where at the exit of that duct the Mach number will become unity. If we try to increase the duct length, then without altering the initial conditions, then the flow will adjust, so that the mass flow rate is decreased, or looking back to our Fano curve in the HS diagram, that the flow will now shift to a different Fano curve to the right, which represents a lower amount of mass flow rate. So, this equation can be integrated from a particular station to this exit condition, or that is the maximum or the optimum critical Mach number, that is unity, where so m equal to 1 corresponds to maximum duct length for given initial conditions and mass flow rate. Maximum duct length will denote as L max. So, we can integrate that 0 to L max for f dx by d. Now, the friction factor in generally will never be available as a function of duct length. However, we can define a mean friction coefficient. We can define a mean friction coefficient mean friction coefficient as if r is 1 by L max to 0 to L max f dx. Introducing this into this integration, introducing this relation in the integration, and the integration can be completed sorry 1 minus m square by gamma m square plus gamma plus 1 by 2 gamma log of gamma plus 1 m square by 2 into 1 plus gamma minus 1 by 2 m square. And this can also be written sometime in this form, that is the maximum value of for given m. Hence, we can write the length of duct L required for the flow to pass from M1 to M2. That is, if we have at a certain section flow Mach number as M1, then what will be the length for the flow Mach number is M2, that can be obtained using this relationship. Writing this for M1 and M2, you can write that for F bar L by D L max by 2. This we can find that what would be the maximum length required from for a flow from reach to unity from M1, which is given by this, and the length required, maximum length that you can have for the flow to reach unity from M2, and the difference of the two will give simply the length required for the flow to reach M2 from M1. So, we can very easily find what would be the length of a duct required if we want to accelerate the flow, accelerate in case of a subsonic flow or decelerate in case of a supersonic flow from a Mach number m 1 to a different Mach number m 2. If we combine equation 8 and 9, combining equation 8, that is dP by P, and equation 9, that is dm square by m square, to eliminate four f dx by d. What we get essentially is dP by P equal to minus 1 plus gamma minus 1 m square by 2 m square into 1 plus gamma minus 1 by 2 . And again integrating this, we have P by P star, where P star is the pressure, where Mach number is unity in this flow with friction. So, this P star, as we mentioned earlier, is different from the P star that we obtain when the flow isentropically reaches unity. Is 2 into 1 plus gamma minus 1 by 2 m square. Similarly, using other equations to eliminate 4 f dx by d in favor of dm square by m square, and then integrating from m to 1, that is we take 2 or 3 such equations, and from them we eliminate 4 f dx by d and in favor of dm square by m square, and then integrate the obtained relation from m equal to m to infinity to unity, and we will get for different parameter u by u star m into gamma plus 1 divided by 2 into 1 plus gamma minus 1 by 2 m square T by T star, which correspond to a square by a star square rho by rho star, which is from continuity in a uniform duct, is two into 1 plus gamma minus 1 by 2 m square by gamma plus 1. The remaining two parameters, that is stagnation pressure, where the Mach number is m divided by the stagnation pressure at the end of the duct with maximum possible length, that is where Mach number is unity, is 1 by m two into 1 plus gamma minus 1 by 2 m square to the power gamma plus 1 by gamma minus 1 divided by gamma plus 1, and also f by f star and for the entropy, the maximum entropy two m square into 1 plus gamma minus 1 by 2 m square whole to the power gamma plus 1 by gamma. Sorry, gamma minus 1 by gamma. More clearly, gamma minus 1 by gamma. Often it is important to find the pressure ratio between two stations where Mach numbers are m 1 and m 2. And that can very easily be obtained from these relations, that is to find flow parameters at a station where m equal to m 2 from known conditions at 1 where m equal to m 1. These relations can very easily be used in this fashion, that say P 2 by P 1 can be obtained as P by P star at m 2 by P by P star at m 1, and similarly say P 02 by P 01 is P 0 by P 0 star at m 1. And similarly other relations and that completes our solution for flow through a uniform area duct with friction when the flow is approximately adiabatic, that is when the duct is short. Hence, to summarize this lectures that flow through a uniform area duct with friction, what we have seen that when friction is the driving mechanism of the flow and no shaft work is done, if the duct is short, the flow can be approximated as adiabatic flow. However, if the duct is long, then there is enough scope of heat transfer through the mechanism of friction and the flow cannot be treated as adiabatic, but it can be approximated as isothermal. With these basic assumptions, we have also assumed that the flow is one dimensional, that is, we are considering the average flow properties at any particular cross section. We have seen that in the HS diagram for a given mass flow and stagnation enthalpy, there is a curve of general shape for all fluids and it has two branches. Since in adiabatic flow the entropy cannot be reduced, the flow will always move towards increasing entropy, that is, on a particular Fano curve the flow will always move towards right, it cannot turn back, that is, irrespective of subsonic or supersonic flow, the flow approaches towards sonic condition. Otherwise, that is, a subsonic flow accelerates towards sonic flow, and if sufficient length is there, that is a for a, of course, the length is fixed for a given h naught and mass flow rate, then at the exit flow can only reach sonic. Similarly, a supersonic flow also decelerates and maximum minimum Mach number that it can have is sonic. Since the flow is adiabatic, total enthalpy and total temperature of course remain constant. However, we have seen that the other parameters of course changes and the change is such that the stagnation pressure always decreases in both cases, whether it is subsonic flow which is accelerating subsonic flow or decelerating supersonic flow, the stagnation pressure will continuously decrease. So, will be the impulse function, and from which we can conclude that the presence of friction in a duct, we will reduce the overall effectiveness of the fluid machinery or flow machinery. The other parameters of course, behave differently in different flow regime. In the subsonic flow, which accelerates towards sonic, the pressure, temperature and density they decreases. However, Mach number and flow velocity increases, while in supersonic flow the opposite happens, that is the pressure, density and temperature increases, our Mach number and velocity decreases. We will now consider, or next we will consider flow in long ducts. Next we will consider flow in long ducts, and as we mentioned earlier, there is again we will consider no external shaft work. However, duct being long, so enough scope of heat transfer by the mechanism of friction. So, the flow is non-adiabatic, but over a length it becomes approximately isothermal. Over a length, the flow becomes approximately isothermal. And this type of flow is quite common in natural gas transport. pipelines for transport of gas, over a long distance. However, we will continue this discussion in our next lecture.